We learn to count early in life. From the moment we can hold up our fingers, we start to understand the concept of numbers. It's a fundamental skill that forms the basis of our understanding of the world around us. 1, 2, 3, a simple, logical progression. These numbers are more than just symbols. They represent quantities, order, and structure. They help us make sense of our environment, from counting toys to understanding time. We add these numbers, subtract them, and the world seems to make sense. Arithmetic becomes a tool we use daily, whether we're calculating the cost of groceries or figuring out how much time we have left in the day. 2 apples plus 2 apples will always equal 4 apples. This simple equation is a cornerstone of our understanding of mathematics. It's reliable, predictable, and gives us a sense of control over our surroundings. The rules are clear, the answer is predictable. Mathematics, in its basic form, is a language of certainty. It provides us with a framework to solve problems and make decisions with confidence. But what happens when we start adding not just apples but infinities? The concept of infinity challenges our understanding of numbers and their behavior. It's a leap from the finite world of everyday math to the boundless realm of the infinite. This is where the familiar ground of everyday mathematics begins to shimmer and distort. The rules we thought were unbreakable start to bend, and the clear answers we relied on become elusive. The comfortable laws we relied on start to bend, revealing a universe far stranger and more wondrous than we might imagine. In the vastness of space and the complexity of the cosmos, mathematics takes on new dimensions and meanings. We enter the realm of infinite series, where the sums never truly end, and where the very act of rearranging numbers can lead to different answers. How can this be? The idea that an infinite series can be manipulated to produce different results is both fascinating and perplexing. How can changing the order of addition change the result, especially when dealing with an infinite string of numbers? This phenomenon, known as the rearrangement theorem, defies our intuitive understanding of addition and challenges the very foundations of arithmetic. Fasten your seatbelts, dear reader, as we embark on a journey into the mind-bending world of infinite series. This journey will take us through the history of mathematics, exploring the minds of great mathematicians who dared to venture into the infinite. We'll uncover the mysteries of convergent and divergent series and see how these concepts apply to real-world problems and theoretical physics. Our journey begins with the pioneers of mathematics like Euler and Gauss, who laid the groundwork for our understanding of infinite series. Their contributions have shaped the way we think about numbers and their infinite possibilities. One of the key concepts in the study of infinite series is convergence. A series is said to converge if the sum of its terms approaches a finite value as more and more terms are added. This idea is crucial in many areas of mathematics and science. On the other hand, a series is divergent if its sum grows without bound. Divergent series can be more challenging to work with, but they also offer unique insights into the behavior of numbers and functions. Consider the harmonic series, which is the sum of the reciprocals of the natural numbers, 1 plus 1/2 plus 1/3 plus 1/4 plus. This series is divergent, meaning its sum grows without limit. Yet, it plays a significant role in various fields, from number theory to physics. The rearrangement theorem tells us that if a series is conditionally convergent, we can rearrange its terms to get different sums. This counterintuitive result shows that the order in which we add terms can drastically affect the outcome. The Riemann series theorem extends this idea, stating that any conditionally convergent series can be rearranged to converge to any given value, or even to diverge. This theorem highlights the delicate balance between order and chaos in the world of infinite series. Infinite series are not just abstract concepts, they have practical applications in many fields. In signal processing, for example, Fourier series are used to analyze and reconstruct signals. In quantum mechanics, infinite series help describe the behavior of particles at the smallest scales. Numerical methods are often used to approximate the sums of infinite series, especially when an exact solution is difficult or impossible to obtain. These methods allow us to harness the power of infinite series in practical computations. The study of infinite series reveals the beauty and complexity of mathematics. It challenges our perceptions and expands our understanding of what is possible. As we delve deeper into this fascinating world, we uncover new layers of meaning and discover the interconnectedness of mathematical concepts. So as we look up at the night sky and ponder the infinite, we are reminded of the boundless possibilities that mathematics offers. It is a journey of discovery, a quest for knowledge, and an exploration of the unknown. Join us as we continue to explore the wonders of mathematics, where every equation is a doorway to a new adventure, and every number holds a secret waiting to be uncovered. The journey into the infinite has just begun. In our everyday world, we deal with finite sums. We encounter them in various forms, whether it's balancing our checkbooks, calculating the total cost of groceries, or even determining the number of hours we work in a week. These sums are straightforward and manageable. We add a limited number of items and we arrive at a concrete answer. For instance, when we count the number of apples in a basket or the total amount of money in our wallet, we are dealing with finite sums. These sums have a clear beginning and end, making them easy to understand and compute. 5 plus 7 equals 12. Simple. This simplicity is what makes finite sums so accessible and useful in our daily lives. We can rely on them to give us precise answers that help us make decisions and solve problems, but an infinite series throws that finite thinking out the window. Unlike finite sums, infinite series challenge our conventional understanding of addition and summation. They introduce a level of complexity that can be both fascinating and perplexing. Imagine adding numbers forever, without ever reaching a final definitive sum. This concept might seem abstract and difficult to grasp, but it is a fundamental idea in mathematics. Infinite series are used to describe phenomena that cannot be captured by finite sums alone. This is the essence of an infinite series, an endless sequence of numbers added together. These series can represent a wide range of mathematical and real-world phenomena, from the behavior of waves to the distribution of prime numbers. We represent these series with a telltale symbol, sigma, the Greek letter sigma. This symbol is a powerful tool in mathematics, allowing us to succinctly express the idea of summation over an infinite sequence. This symbol signifies summation, the process of adding the terms of a sequence. By using sigma notation, we can write complex series in a compact and understandable form, making it easier to analyze and manipulate them. But unlike a finite sum with a clear endpoint, an infinite series stretches on indefinitely. This infinite nature can lead to surprising and counterintuitive results, challenging our intuition and pushing the boundaries of mathematical understanding. The challenge lies in understanding what happens as we keep adding more and more terms. Does the series converge to a specific value, or does it diverge, growing without bound? These questions are at the heart of the study of infinite series. Does the sum grow infinitely large? This is a key question when dealing with infinite series. Some series, known as divergent series, do indeed grow without bound, leading to infinite sums that cannot be easily interpreted or used in practical applications. Does it settle towards a specific value? Other series, known as convergent series, approach a finite limit as more terms are added. These series can be incredibly useful in mathematics and science, providing precise values for complex calculations. Or does it do something even stranger? Some series exhibit behavior that is neither purely convergent nor divergent, leading to fascinating and sometimes baffling results. These series can oscillate, change direction, or exhibit other complex behaviors. To unravel this mystery, we need to explore the concepts of convergence and divergence. Understanding these concepts is crucial for working with infinite series and applying them to real-world problems. By studying the behavior of series, we can gain insights into the underlying patterns and structures that govern the mathematical universe. In the classroom, students often encounter infinite series for the first time in calculus. This branch of mathematics provides the tools and techniques needed to analyze and understand these series. Through calculus, students learn to determine whether a series converges or diverges and how to find the sum of a convergent series. Textbooks and lectures introduce various tests and criteria for convergence, such as the ratio test, the root test, and the integral test. These methods help students systematically approach infinite series and make sense of their behavior. The study of infinite series has a rich history, with contributions from some of the greatest mathematicians of all time. Figures like Leonhard Euler and Carl Friedrich Gauss made significant advances in our understanding of series, developing techniques and theories that are still used today. Today, mathematicians continue to explore the properties and applications of infinite series. These series are used in a wide range of fields, from physics and engineering to economics and computer science. They provide powerful tools for modeling and solving complex problems. One of the most famous applications of infinite series is in Fourier analysis. This technique decomposes complex signals into simpler components, allowing us to analyze and manipulate them with greater precision. Fourier series are used in everything from audio processing to image compression. Another important application is in Taylor series, which approximate functions with polynomials. These series provide a way to represent complex functions in a simpler form, making them easier to work with and analyze. Taylor series are used extensively in numerical analysis and scientific computing. Power series are another type of infinite series with wide-ranging applications. They are used to solve differential equations, model physical systems, and even in the development of algorithms for computer science. The versatility of power series makes them a valuable tool in many areas of mathematics and science. As students and mathematicians continue to explore the world of infinite series, they uncover new insights and applications that push the boundaries of what we know. The study of these series is a testament to the power and beauty of mathematics, revealing the intricate patterns and structures that underlie our universe. Infinite series may seem daunting at first, but with patience and perseverance, they reveal a world of endless possibilities. By embracing the challenge, we can unlock new levels of understanding and appreciation for the mathematical wonders that surround us.